Hello guys, this is Prime Concept. Now we want to do the concluding part of capacitors, right? Which is dielectric. So in this video we'll be learning what a dielectric is, we'll be learning what we call dielectric breakdown, and we'll be learning the effect dielectric would have in capacitors, right? Parallel plate capacitors. Now, if you have been following my videos, if you have been following my channel, do well to hit the subscribe button. Subscription is actually free, so subscribe so that you can always be the first to be notified whenever I post new videos, right? Like my videos, comment, and share with your friends so that they can also benefit. This is Prime Concept. I want to analyze dielectric, so let's move into the business for the day. Now, when we started studying the concept of capacitors, we mentioned that capacitor is an arrangement of two parallel plates such that the plates are separated at a certain distance, right? And then in between there is nothing separating them. And we mentioned that if there is nothing separating the plates of the capacitor, then it simply means that the capacitor plates are separated by air, by vacuum. That's what it means. And under that scenario, we mentioned that the capacitance of a capacitor when the plates are separated by air is given by C equals epsilon naught A divided by D. So for the sake of including a dielectric, so we're going to call the capacitance of a capacitor when the medium of separation is air. We're going to assume the capacitance to be C naught. So what it means is that C naught is capacitance in air. So when the medium of separation between the plates is air, it means that the capacitance will be considered as C naught. Remember, epsilon naught is permittivity of free space. Now, if you want to improve the performance of a capacitor, it's always ideal to insert some materials, insulating materials between the plates of a capacitor. Now, this insulating material can serve mechanically as a means of separating the plates of the capacitor so that both conducting metals do not come in contact with each other. Like I mentioned, if those plates come in contact with each other, it will cause a spark, right? So in order to avoid that, it is always ideal for a real capacitor that some materials, insulating materials, are placed in between the plates of the capacitor to separate them. Now, those insulating materials that are placed in between the plates of the capacitor so that the capacitor plates don't touch each other, those materials are known as dielectric materials. So for the sake of definition, what are dielectric materials? Dielectric materials are materials that do not allow electric charge or electric currents to pass through them, but can allow electric field to travel through them. So they don't allow currents to flow, but they can allow electric field to be transmitted through them. So those materials are what we call dielectric material. Now, if we consider a case where we have a capacitor with a dielectric material, what it means, according to Michael Faraday's experiment, that if you have a capacitor that has a dielectric material, that the capacitance of that capacitor C would be increased by a factor. So the capacitance for that capacitor now would be K times the capacitance of the capacitor when the medium of separation is air. So it means automatically that dielectric materials increase or improves the capacitance of the capacitor by a constant K. And what do we call K? K is known as dielectric constant. So the capacitance of every capacitor would increase by what we know as what? Dielectric constant. So this is what Michael Faraday told us, right? Now, we want to look at how this can also affect other capacitor quantities like the potential difference across the plates of a capacitor. Now, say we have, if you recall, we have that Q is equal to CV. Now, if the charge, of course, is maintained, the charge is kept constant. So what it means is that the charge, when there is a dielectric, is simply going to be Q equals CV, right? With dielectric. So with dielectric, we're going to have Q equals CV. And when the medium of separation is air, and then the charge is maintained constant, it means we're going to have that Q, since the charge is kept constant, we do it in such a way, we insert dielectric material in such a way that the charge is not lost, right? So Q is going to be C naught V naught. So if I equate these two quantities, I will then have that CV from above equals what now? C naught V naught, right? Now, and if you recall, C, the capacitance with dielectric, C is actually K times C naught. So I'm going to simply replace that here. So I would have K times C naught V equals what? C naught V naught, right? So if you observe this relationship, you'll notice that C naught can fizzle out. C naught would go. Then I would have that V becomes V naught divided by K. So this is also a relationship for the potential difference. And this goes to say that the potential difference across the plates of a parallel capacitor would always decrease by a constant, which is the dielectric constant, right? So that is what this also implies. Then thirdly, we want to get the relationship for the electric field. How will the capacitance, how will the dielectric affect the electric field that moves across the capacitor plates? So thirdly, we would have, if you recall, notice that V, electric field, V is equal to ED. So if this is the potential difference when there is a dielectric, between the plates, this is the potential difference, V equals ED. So it means that in air, we're going to have V naught, right? Equal to what now? E naught times D. The distance of separation is constant, of course, is kept the same. So if I substitute now, remember I have that V is V naught divided by K. So I'm simply going to replace that. Let me just call this equation 1 and then these two. So I'm going to replace V in equation 1 with V naught by K. And then I would have V naught from equation 1 by K equals ED, right? Yes. Now, if I make V naught the subject here, I would have that V naught becomes KED from this, right? V naught is then KED. And see what I'm going to do. Since V naught is KED, and we also know that V naught is ED, I'm going to equate both of them. So if I call this equation 3, I'm going to equate 2 and 3, so that I would have that KED equals what now? Equals E naught D. So what are you observing from this relationship? You would also observe that D would fizzle out. And if I make E the subject, I would have that E becomes E naught divided by what? K. So this is our third relationship, right? So what this thing means is that the capacitance of a parallel plate capacitor will increase by a dielectric constant K. The potential difference will be decreased, right? When there is dielectric, the electric field would also be decreased. Now, if we have an arrangement of capacitor, a parallel plate capacitor that is insulated by a dielectric material. Now, at a certain potential, when the voltage across the parallel plate keeps increasing, you get to a point where the electric field between the plates becomes so large such that the insulating material becomes ionized, and then it begins to allow electric fields to travel across it. Under the condition where the dielectric material becomes ionized and then can permit electric field to now travel through it, under that condition, we say the dielectric material has experienced what we call dielectric breakdown. So when the potential difference becomes too high, the dielectric material would experience what we call dielectric breakdown. So what is dielectric breakdown? Dielectric breakdown occurs when a dielectric material can no longer withstand the electric field. So that is what you call dielectric breakdown. So take note of the three conditions we have mentioned for a capacitor when dielectric materials are there. So one of the basic things you should take note of is that the presence of dielectric increases the capacitance of a capacitor. I believe this concept is very clear to you. If you have been getting values from my videos, please do well to subscribe, follow, click the like button, comment, share with your friends so that they can also benefit. Remember, this is Prime Concept. Thank you.